All right, here we have an old IB Math Paper 1 question. It's a displacement velocity acceleration question. IB loves to ask these, so it's really important that we practice them together. Notice that it's a question number 3 from an old exam, so it appears pretty early on, which means it's not going to be one of the most difficult questions they could ask on this topic, but it's good that we practice them anyway. So let's get to it. Part A is asking us to find an expression for velocity of the particle given that they give us the expression for displacement of a particle. Whenever we see the words displacement, velocity, and acceleration, always what we're going to think about is derivatives every single time. Remembering, I'm going to do a little chart for us to keep this in mind, that if we have displacement, I'm going to just write dis, and I want to figure out velocity, I take the derivative. If I have velocity and I want to figure out the acceleration, I take the derivative. In a different unit, when we talk about integration, we can go the other way around. If I have acceleration and I want to go towards velocity, I would take the integral. And if I have velocity and want to figure out displacement, I take the integral. But right now, they give us the expression for displacement, and we are asked first to figure out velocity, and we'll see in parts B and C, figure out the acceleration afterwards. So we're going to be taking a lot of derivatives for this question. Okay, let's erase this so we've got a bit more nice, clean space to work with. Let's get to it. All right. We have an expression for displacement. S is equal to the ln natural logarithm of 2 minus e to the negative t. And we said, okay, well, to figure out the displacement, we need to take the derivative, or the velocity, excuse me, we need to take the derivative of displacement with respect to time. So we use this notation ds dt. I'm going to rewrite this as the d dt, the derivative with respect to time of the original function that we were given, 2 minus e to the negative t. Okay, we need to remember some of our basic but fundamental derivatives now. Remembering that the derivative of something like ln of t or ln of x, whichever kind of function, the logarithm or natural logarithm ln is just 1 over t. So we're going to kind of use that property, use that fundamental derivative to figure this one out. I'm going to delete this or erase this and move on. So the derivative of this specific function is going to be equal to 1 over whatever I see on the inside of the logarithm, 2 minus e to the negative t. But hold on, we got a chain rule here we got to work on, okay? Whenever we're taking the derivative of anything, really, we have to think about what's the derivative, the basic functional shape of the derivative and the derivative of the inside thing. So to complete the chain rule for this one, this would be the derivative, or would be 1 over 2 minus e to the negative t times the derivative of the inside. Okay, so let's work on that for a second. In fact, let's do it in blue. This blue is nicer. The derivative of the inside of this 2 times e to the negative, or 2 minus e to the negative t, we can figure out with just some power rules. The d dt of 2 minus e to the negative t, well, derivative of a constant is 0, so that goes away. And the derivative of e, we know the derivative of e to the x is e to the x, but there's a negative sign in the exponent. So that also has a chain rule we need to take into account. So this would be negative e to the negative t times the derivative of negative t, because that's what's in the exponent. Well, the derivative of negative t, if we're taking it with respect to t, is just negative 1. So that literally just gives us e to the negative t. So we got to go back up here and say, well, the derivative of this whole function then, of ln of that thing, is 1 over 2 minus e to the negative t times e to the negative t, which is, if we simplify it out, e to the negative t over 2 minus e to the negative t. This would be an expression for the velocity of this particle. I know it's confusing, or I know it sounds confusing with all these negative t's and e's and stuff floating around in chain rule, but remember, every kind of principal kind of function is going to have the same derivative shape. ln of something, 1 over that something. E to the x, just e to the x. The derivative is itself. But you always have to take into account what is being plugged into these equations, because that's going to help us dictate what the chain rule component, that extra little step we have to take to make the derivative nice and crisp. That's part A. Part B, let's see. Now we find the expression for acceleration of the particle. Remember from earlier, all we do now is we take the derivative of the velocity. So in this particular case, the acceleration of the particle is going to be equal to the derivative of the velocity with respect to time, dv dt. I'm going to rewrite this again as the d dt, the derivative with respect to time of the expression that we literally just came up with from the previous part, e to the negative t. So we're taking the derivative of e to the negative t over 2 minus e to the negative t. Jesus, so many e's to the negative t's. With respect to time. Okay, to do this, for this one, we notice that we have a ratio or a quotient of two functions. We've got a function, e to the negative t, on the top of that fraction, and we've got 2 minus e to the negative t on the bottom. So whenever we have a fraction with a variable on the top and on the bottom, we use the quotient rule. Quotient rule. Nice. This is a nice little shortcut for us to figure this. It's basically like an embedded chain rule. Helps us figure this out. To do this, we're going to rewrite this function, or I'm going to pretend this function is written in such a way that the top is a u and the bottom is a v. That'll help us. As a little reminder for what the chain rule is. The chain rule tells us the derivative with respect to t of two functions, let's call them u, like we had earlier, and v, is going to be equal to the derivative of the first function. I'm going to use shorthand notation for this. Derivative of the first function times the second function, or the bottom function, minus the first function times the derivative of the second function, all divided by the squared of the second function v. So we literally just have to plug this in. We'll use with the values from our function, and we've taken the derivative. Don't worry if you don't remember this off the top of your heads. This is in your formula booklet for both the HL and the SL, so you're fine. Okay? So let's figure this out. Well, in fact, you know what we're going to do? We're going to figure out the derivatives over here off to the side to start with, so we can just literally plug and chug. The derivative of u, the top one, like we said earlier, is just going to be, or in other words, the derivative of e to the negative t is just negative e to the negative t. It's the derivative of the exponent times itself, because that's the fundamental derivative of the natural number, Euler's number e. The derivative of v, of the bottom thing, well, is going to be the derivative of, I'm just going to rewrite it so we have it here, nice and written for us, prime. Derivative of 2 goes to 0. Nice. So we're literally just left with e to the t. Beautiful. Let's all plug this in. Using this quotient rule, u prime negative e to the negative t times v, 2 minus e to the negative t. Okay. I notice now I'm going to need more room, so I'm going to delete that for a second. I think that should be good. Minus, we're now going to focus on this part. U from the previous question is just e to the negative t times v prime, which we figured out here, e to the t, all divided by v squared, 2 minus e to the minus t squared. Now that we're here, we've plugged into our quotient rule, we can start simplifying. To simplify this, I think the nicest thing we can do is distribute out this e to the negative t. So we end up with negative 2e to the negative t plus 2 minus and a minus make a positive, e to the minus 2t, and then these two terms would be a minus e to the negative t minus e to the times e to the negative t gives us an e to the negative 2t. We're going to see that those two terms are going to cancel themselves out. I'm not going to do anything to the bottom term because we don't need to, because here we see those two terms is like the same thing as saying 1 minus 1. They just cancel out to 0. The same term minus itself gives me 0. So the only thing that I'm left with on the top of this fraction is negative 2 times e to the negative t over 2 minus e to the negative t squared. And that is our expression for the acceleration. Part B, done. Now, part C is perhaps the easiest. Find the acceleration of the particle at time 0. These questions are awesome because they're free points. The acceleration at time 0 literally just means we plug in a 0 into that new expression we have for t and see what it spits out. Okay, let's just rewrite the whole thing, but every time we see a t, we're going to write into 0 times 2 minus e to the negative 0 squared. Okay, I've plugged it in. E to the 0 is just going to give me a 1. So on the top, I have a negative 2. And on the bottom, I would have a 2 minus 1. This is a 1. So 2 minus 1 gives me a 1. 1 squared is 1. So the acceleration of the particle is minus 2. That's it. If you like this and you want more content, subscribe, follow. More to come.